Hello, members of 7th grade. Thought, last day of the work week, let's do an investigation. It's something that they might start asking you about, already maybe have, so we want to make sure we're playing catch up on that. So this is investigation 8. We're going to be looking at probability and odds. We're going to spend the first part of the lesson talking about probability issues, and then we're going to close out with odds. So there's two major things we have to cover in probability. One is something called compound events, which we have discussed. And then the second is experimental probability, which we have discussed and even kind of played out in that, I think it was Yahtzee last year. So if you weren't here last year, we did a project on experimental probability using the game called Yahtzee. Let's talk real quick about what compound events. Basically, compound events are when there are more than one event. And we're going to play out a couple situations. But if there's more than one event, not just me doing one thing, like flipping a coin or pulling a card, if I'm doing two things, then that is considered a compound event. And as we learned about experimental probability in the past, experimental probability is one, it's not theoretical. And then the second thing we need to understand is that we actually do the thing. We actually test something out, right? We do the event, often many, many times to ensure, yeah? Okay, so let's remind ourselves how basic probability works. So the probability of an event, we know is always, I always consider the number of possible outcomes first. I know we've done this before, but let's just resetting, making sure we're on board. And then we know that what comes in the top of our ratio is the number of favorable outcomes. Yeah? And we've done that scores of times. We're moving ahead. We're building upon that. Let's talk about compound events. Now, as I said, compound events are when there's more than one thing. And so there's kind of a principle or theory that supports this. So the probability of A and B occurring, the A being one event and the B being another event, is equal to the probability of A. And then there's the probability of B. And then do you remember what we do with this? Yeah, good. We multiply. Yeah, we multiply those. And that'll give us the compound probability, if you will. So imagine I had a coin. This is my coin. And imagine I had one of these, a spinner. And I asked the question, hey, what's the probability of me getting, we know the H means heads, and a 4 on the spinner? So this is clearly a compound event. Why? Well, there's two things going on. I'm flipping a coin and I'm spinning a spinner. That's a compound event whenever you have two or more events. So as we talked about, if we're going to consider the flipping of the coin, we'll call that the probability of the A. We know whenever we flip a coin, the probability of me getting the heads is a 1 to 2, right? We've looked at that many times. And then, so the probability of the B thing, well, the B would be the spinning the spinner. And obviously the probability of me landing on 4 would be, because there's 4 equal parts, would be 1 to 4. And remember what we do with these, as we know, we are going to multiply those. So then obviously they're multiplying ratios, but I look for cross-canceling, there is none. And I come up with 1 to 8. Yeah, the probability of me flipping a coin, getting the heads, and spinning that spinner, and getting a 4 is simply 1 to 8. Let's look at another compound event. Because the whole thing is, it doesn't have to be like different things. Like, you don't need a different item. Because if I was to take a coin and flip it 3 times, well, that's 3 events. So what if I was to do that? Or even just take 3 coins all at once and flip them all at once. In the end, those are all 3 different events. So if I think about the first event when I flip that coin to get a heads, well, that's clearly 1 to 2. Well, there's still yet another event. I flip it, it's 1 to 2. And yet there is still one more event. I flip it, and I get 1 to 2. And then I'm ready to go. I've represented probability of A, probability of B, and in this case, probability of C. Therefore, the probability of me getting 3 heads in a row is simply 1 to 8. Now, I want to explore the fact that everything we've talked about, so write down, so far, everything we've talked about has been only independent events. And independent events always come up with things like coins. Whenever I flip a coin, it's an independent event. I could have literally gotten 100 heads in a row. It doesn't necessarily increase the probability that I'm going to get a tails. I'm likely to, but, it's still 1 to 2. What else? Die, or dice. That is always independent. It's always 1 to 6 of whether I'll get a 6. Another thing would be spinners. So again, when I walk up to that spinner, and the last one we looked at, it's 1 to 4. If I would say, what's the probability of getting even, it would always be 1 to 2, right? So those are always independent events. However, there are other types of events, and I know you know about these. They're called dependent events. And basically, a dependent event is when the first event affects the next event. And laughingly, I always kind of think about like maybe going to a party, and at some point they call the people to the tables to have dinner, but you kind of like got to go up through the line, and maybe you were talking to someone and the line started to form behind you, and you'd walked by the plates before it and you saw a bunch of sandwiches, but there were different sandwiches. There was like roast beef, there was ham and Swiss, there was turkey, and you wanted the roast beef. Well, if you get in the back of that line, the probability of you getting the roast beef is going to be affected by every person who grabs at that plate. One person grabs roast beef, my likelihood has gone down. Another person grabs roast beef, my likelihood is disappearing, right? So that's what I often think about with dependent events. However, we could think about marbles in a bag. So we've done this a lot. So let's say we had in a bag 3 green marbles, 5 blues, and let's go with 2 purples. And as we played this out before, maybe I asked the question of, hey, what's the probability of me getting not just 1 blue, but how about 2 blues? And here's the key. In order to make this a dependent event, it has to be what's called without replacement. So again, if I walk up to you with this bag and you reach in for a blue, well, that's going to be a certain probability. And then if I say, hey, give me the marble back, well, then you've replaced the marble back in the bag, and the next person is simply going to be dealing with the same probability. However, if I'm like, give the marble back, and you're like, no, I'm going to hold on to my marble, well, then that's without replacement. So things shift. So if we think about the first event, one, we have to think about number of possible outcomes. So I have 3 plus 5, that's 8 plus 2. So there's 10 possible outcomes. If I'm interested in the blue, well, there's 5 favorable outcomes, right? There's 5 blues. Now, again, here's the kicker. You're not replacing the marble. You're holding on to it. And one thing you have to remember is, one, we're going to multiply, and without replacement means that what has changed? Well, a couple things have changed. One is the number of possible outcomes. Is it still 10? No, because the bag started out with 10 marbles, and one has been taken away and selfishly not returned, not replaced. Therefore, I'm not at 10 anymore. I'm actually now at 9. Now, the other thing is, and here is a kicker, we always have to assume that the first event happened. So we assume the first person got the blue. Yeah, they're not giving it back to us. We know they're holding on to a blue. So not only did my possible outcomes shift, what about my favorable? Is it still 5? Are there still 5 blues? Well, no, not if we assume that someone has one. So when we think about our favorable, now it's shifted from being 5 to 4, because now there's only 4 blue marbles. All right, that's probability of A times probability of B. So now we'll do some cross-canceling. I see that 4 and 10. I'll call the 4 2, the 10 5. Oh, I got 5 over 5. Well, that's clearly just 1, right? So when I multiply straight across, I end up with a probability of 2 to 9. And I box that up. Yeah? All right, now we get to talk about experimental probability. This is getting a little long, but we're going to be fine. I'm going to try and speed it up. So there is a difference in the language for experimental probability. One is the probability of an event is not about the number of possible outcomes, but it does have the number of, it's called the number of trials. And the trials is the number of times we did the thing. It's also not the number of favorable outcomes. What it is, it's the number of times that the event occurs. So this can be done in different ways. One of the things they use it for is what's called product testing. And so let's say there's a company who created, 10,000 products. But they know that every once in a while, one of their products goes bad. It's defective. So how many are defective? Well, what they can do is they can do experimental probability. To test all 10,000 is ridiculous. So what they do is they're just going to test 100 of their products, 100 of those 10,000. Those are my trials. Then in that test, they found that 7 were defective. So that is the event occurring, it being defective. Because if I ask, what's the probability of one of these things being defective of my 10,000 or of the 100 I tested, I know that the number of trials is 100 and the number of times the event occurred was 7. So therefore, the probability of one of them being defective is 7 to 100. Now, in order to find out how many are defective of the 10,000, I can take that 7 to 100 and I can multiply it by 10,000. I got some nice cross-canceling, boom, boom. And then I just got 7 times 100. So that would mean that 700 are likely to be defective. It's not theoretical. I'm not just going, oh, how many times? Like, again, when we flip the coins. And so if you think about that idea, and I want you to think about that for a little while. If I flip a coin, it's 1 to 2 that I get a heads, right? Well, do I always get a heads every other time? What about if I flip it 10 times? Wouldn't I expect it to be 5 heads and 5 tails? Does that always happen? We're going to talk about that. But let's dive into odds real quick. Odds is sadly a little bit confusing. And sometimes people not in the math world, they'll use probability and odds interchangeably. And there's enough elements of how we figure out odds that is similar to how we figure out probability. So all I can say is, be careful. There are 2 types of odds. One is what we call odds in favor of something. Sometimes it's just called odds for an event. So there's also odds against. So I also want you to write. So odds for. That means the same thing as odds in favor. And here's the thing. If we are going to think about odds in favor, or the odds for something, we think about the favorable outcomes over not the possible outcomes. And that's kind of why it's messed up. It's similar. It's the number of unfavorable. So if I was to take a situation like say, okay, so what's the odds for rolling a 6? Now we know the number of favorable ones is 1. That hasn't really changed. But be careful. I don't want to put down a 6 because I'm not talking about the possible outcomes. I'm talking about the unfavorable. Well, what is unfavorable? Well, the 1 is, what about if I rolled a 2 or a 3 or a 4 or a 5? Those would all be unfavorable. And essentially there are 5 unfavorable outcomes. And so the odds in favor of me rolling a 6 is 1 to 5. Yeah. So odds against just works in the exact opposite way. Instead of putting favorable on top, we're going to put unfavorable on top. So what if I was thinking about like the odds against choosing an ace from a pack of a deck of cards, a full deck. So again, if I'm going to go unfavorable over favorable, well, unfavorable, there's only 4 aces in the deck, and there's 52 cards, so unfavorable would be 48. What is favorable? Well, like I just said, there are 4 aces, so 4 of them are favorable. Can that be reduced? It sure can, but I don't want to reduce it to a whole number. So I would say that the odds against me choosing an ace are 12 to 1. Sometimes we'll see, more often in odds, we'll see this written out, 12 to 1. In fact, a lot of like sports betting uses odds. They consider probability, but the language they use is odds. They'll say the odds of 3 to 2, but they'll usually write that out. Okay, last little point I want to make has to do with that experimental probability. Okay, so we know when we flip a coin that the probability of me getting the heads is exactly, theoretically, 1 to 2. However, if I flipped a coin, let's say, 10 times, we would expect to get 5 heads. Well, if you have a coin, go do it right now. Did you precisely get 5 heads? What about if I flipped it 100 times? We would expect to get 50 heads, right? 50 heads, 50 tails. However, that's not going to be our reality. And that's the difference between what is theoretical, where I simply say, oh, it's 1 to 2 in theory, and the experimental. Because what I would do for the experimental, I'd actually flip those coins. So for the 10 times, maybe I got heads 6 to 10. Well, that's not 1 to 2. Or maybe when I did it 100 times, I started to lower it. I got 42 to 100. Well, that's not 1 to 2. What about if I did it like 1 million times? What do you think's going to happen? So 6 to 10 is not too far off. I mean, it's 10% off. 50 is 8% off. What if I did it a million times? How many heads, or what do you think the probability would be getting closer and closer and closer and closer to? Yeah, you'd be right. 1 to 2. The more I do the experiment, the closer my experimental probability gets to my theoretical probability. So look, doing an event, a trial, like 10 times, look, it doesn't really tell us much at all. I could get 10 heads in a row. And then we'd think, oh, every time you flip a coin, you get a head. So that's not true. So we want to do our experimental. We want a lot of tests. Like even the product at 10,000, they only tested 1%. Is that right? Yeah? I mean, that's not much. So we want to test a lot. Hey, that was a long one. But the good thing about it is the end of our work week. And because it's an investigation, I don't have any homework for you. In fact, what we'll do is we'll do a new lesson on Monday, and then we will, that'll just be that full lesson. So no split. Just wanted you to take some time to consider these very important ideas as we move forward. Hope you're doing well. Reach out to me if you ever need me. Bye.